All right, so I'm going to assume everyone in this room is familiar to some extent with Haskell, but I don't know if everybody has even heard of Racket. I guess raise your hand if you have heard of Racket. All right, has anybody here written any Rackets? Written a little bit. So it's a scheme descendant, but it's very different from, I think, a lot of Lisps. It's not really a language, it's more of a language platform. And so there's been a lot of research into figuring out how to build languages really, really, really fast with using Racket, and one of Racket's main components is this macro system. And it's a very safe macro system. It's really kind of cutting edge. There's a lot of type systems in the world. You can really make arguments about which one's the best. There's kind of a lot of orthogonal type systems, but Racket's kind of indisputably has the best macro system in the world. It's really kind of, there's no competition. There's about 20 years of research going into it. So because of that, one of the things that, this is very, very new research. This is being presented at Popple 2017, type systems as macros, and it's figuring out how to, as the name would imply, embed type checking into macros. And I'm going to kind of connect that to Haskell towards the end. This is not my talk, as you can see. This was given at RacketCon 2016 in September, last month. But I'm going to give it because it's something I have. So basically, Racket, as I've kind of mentioned, is a programming language for creating programming languages. And there's ways to sort of reuse existing constructs. So all these things are sort of like core primitives that you can overload. And you also have the ability to just arbitrarily customize the program semantics, the reader. There's like Algol60 is a language in Racket. JavaScript is a language implemented on Racket just for fun. There's Prolog implemented in Racket, but the main language is the Racket language. So it's kind of two things. It's a language and a Racket and a language platform. And that's a scheme descendant. So Racket really focuses on linguistic reuse. And so basically the idea is if you are interested in building a language, rather than having to build out an entire compiler with compiler architecture, you can just start with something that already exists. And all these languages can kind of talk to each other at a pretty high level, which is really nice. So this is a really simple diagram of, it's a little bit hard to read because it's relatively small, but the basic idea is that these are all the different languages that are in the core of Racket. And if you look, there's a black, which is everything else, so this is not actually all of them. But these are all the languages used to implement the core of Racket. And so these all talk to each other, they all interop very, very nicely with one another. And so the idea is that you pick a language for your specific tool. So languages are just libraries in Racket, and you can use many of them together to make one program. So there's a problem though with these, is that every single one of them is untyped. There's actually one typed language in the Racket ecosystem, which is called, not too surprisingly, typed Racket. And it's a gradually typed version of sort of the Racket language. It does static type checking as a macro expansion pass. And so the way it works is basically you have one big macro that wraps your program implicitly. You expand all the user macros, you check the types, and then you get very strong static type guarantees that you would expect. But it's designed to be gradually typed, so you don't get things like type classes. You don't have unification-based type inference. It's really just designed to be, the flow type system, if you're familiar with the flow type checker for JavaScript, is based on a lot of the research that went into typed Racket. So the question is, can you come up with typed languages in Racket, or is it really only good for one thing? And the good news is you kind of can. So again, here's kind of a diagram of the way typed Racket works. Is you have your typed program, you expand it out, you type check the fully expanded program, and then you run the result with the types erased. So that's a pretty standard way. Aside from the macro expansion pass, this is a pretty standard approach to doing type checking. And so basically, the trouble with this, of course, is that this takes a monumental amount of effort to build. It took years of work. And it's really not possible to reuse, whereas you can reuse faculties from other languages in dynamically typed Racket languages. It's really hard to reuse pieces of the typed Racket type system. So the alternative approach, which again is very, very new, is basically figuring out how to make macros interleaved with type checking. So macros actually do the type checking as well. So you kind of, instead of just having the type checking at the very edge of the program, we push it in as the program expands. So what this lets us do is basically define, this is an example of defining sort of a simple lambda calculus language. So we have a lambda, which binds an x and produces an expression. And this will just expand to the Racket lambda. And then we have sort of application, which has 2 expressions, and we'll just expand into Racket's application. So this is obviously not very interesting because we're just basically reusing the Racket host language semantics. But you can see that we've come up with like a really simple language that has only 2 primitive forms. So what we want to be able to do is type check this. We want to create the simply typed lambda calculus. And it turns out that this is actually really possible to do. But what we want to be able to do is just basically translate the STLC typing rules just from the typing judgments and figure out how to turn those into macros that will actually perform type checking. And it turns out that we can do this. And so it looks kind of like this. This is an example of the type checked application form. Now it looks kind of complicated, and it looks nothing like that typing rule. But it does actually correspond. So the basic idea here is what we're going to do is we're going to type check the type, we're going to get the type of E1. Yes?
What's the procedure for reading those symbols on the right?
Which?
So that block, like
this thing? This is just like on the slide. This is just on the slide. It's not actually source code. This is the source code.
So I'm not supposed to understand that thing.
No. This is the typing judgment. If you're not familiar with like typing rules, that's totally okay. I actually had no knowledge of type theory before I started working on this. So I'm about a month in, and before that, when I saw this talk, I had no idea what any of these meant. So no, you don't have to understand that.
Are you able to explain it right now in real time?
I could, yes. So this typing rule is the typing rule for application. So it basically says, you can read basically every typing rule has 2 parts. It has stuff above a bar and below the bar, and its implication. So it says if all the stuff on the top holds, then the bottom is true. So the way you can read each one of these sort of propositions is you say, in some type environment, and for the most part you can ignore that. It's not terribly important, but it basically says if E1 has type T1 to T2, so it's a function type, and E2 has type T1, then applying E1 to E2 will give you T2. So it's really simple function application. If you've ever worked with a functional programming language, that makes complete sense. So the question is, how do we translate this into macro rules? And again, you're not familiar with Racket scheme syntax, but it's not too bad. The basic idea is we're going to take the first argument, and we're going to type check that we're going to pattern match on the type of that argument, and we're going to say that it's a function type from T1 to T2. Then we're going to get the type of the second argument and say that that's the type of the argument, and then we're going to check that these 2 things are equal. And basically these
can we just go over some of the syntax a little bit? So there's a pattern match. I'm not sure I can read it.
Yeah, so each one of these with clauses is a pattern match. So it says pattern match this to be this thing on the right. When is a condition. So if these things aren't true, the macro expander will backtrack. So what this lets you do is it says, all right, so we're going to get the type of E1, which is the first argument to this checked application, and we're going to destructure it, say that it has this type, an arrow type, and the 2 arguments are T1 and T2. Similarly, this one's just an identifier, so we're doing no destructuring there. It's just a binding. And then this is type equality. So basically we're saying, all right, given that these 2 things are equal, then we'll continue. And now what we're going to do is we're going to perform type erasure. So when you expand a program with types, eventually you produce a program without types, and you send that off to your compiler. And so that's what we're going to do here. We're going to say, all right, erase all the type annotations in those 2 things, produce untyped forms, and then expand into Racket's application again, and assign this piece of syntax the result. And so this thing basically puts a property on this piece of syntax that then type of can read. So in another macro that now consumes this piece of expanded syntax, it can now get the type of this expression. And you don't need to understand all the details of this, but still, if you have any questions, don't hesitate to ask. But the basic idea is, can everybody see how, on some level, this typing rule translates into this blob of code? Okay.
I do have one question.
Yes.
Do you have to explicitly state all types in your program?
You can do type inference. Haven't gotten there yet, but yes, I will.
Quick question. It's
Yep.
pretty simple, but so checked app E1, E2. What does E1 and E2 do?
So this is a macro. So this is operating syntactically. So when basically you have some macro invocation, these are 2 pieces of syntax. They're pieces of the syntax tree. So because this is a Lisp, this is really easy to do, because they're just big trees of parenthesized expressions. So basically this is, when you actually use this, it would just look just like this. It's a pattern matching form. So it says basically like you would have checked app, and maybe this is a function expression and this is an argument expression, and you'll get hold of these pieces of syntax in basically in the body of this macro.
So this is just type checking, sort of the lambda calculus always just has one argument, that's why it's E1, E2, and very well.
Exactly. So really this is F and this is X.
Got it.
Okay. So then the question, of course, is why can't we translate this more directly into this? Because this is a really weird translation, and it's kind of complicated. So it turns out that you can do this, and this is because Racket is really kind of incredible. In the sense that Racket is really a programming language that is designed for building domain-specific languages. And in fact, it has a domain-specific language for building domain-specific languages called syntax parse. And it's amazing. And if you're interested in building languages, I would highly recommend checking it out. But that's a separate talk, and not particularly related to Haskell. So the question is, how can we translate this more directly? And it turns out that we can totally do better than this, because we can come up with sort of a domain-specific language syntax for more directly translating typing judgments into macros. And so this is a macro-defining macro, and you can do that in Racket very easily, because Racket has a very specific notion of lexical scope, which is known as hygiene. It's sort of a formalization of lexical scope. So macro defining macro is totally okay. You can do that, and the macro system handles it no problem. So what we're able to do now is we're basically going to say, we're going to translate each one of these rules pretty much directly. We're going to say, given that, you can read this as, so here's the input to our macro, E1 and E2. Given that E1 expands to E1 without types, so that's doing the type erasure pass, and has a type that we're going to pattern match on, which is T1 and T2. Similarly, E2 expands to E2 prime, which is E2 without types. And then we have sort of this T1. Now, our pattern matching language here isn't as powerful as our notation. So we can't just directly say like these two things are equal, because that would be binding an identifier twice. So we have to introduce another step right here that says that they're the same. But then we have the result, and we're basically just saying, all right, so now we're going to expand to this, and it has type T2. And this macro will handle the rest. But we can do better than this. Because we can actually extend our pattern matching language so that we don't have to introduce that extraneous when clause, and we can actually just specify it directly. And it will understand that this is a type binding, and so it'll actually insert the type quality check here. But we can do even better than this. Oh, and one thing that's important to recognize here is we have these arrows which don't appear in the typing rule. The typing rules themselves are bidirectional by nature. By saying basically like here that this is T1 to T2 and this is T1, there's an implicit understanding that there's some check that those two things are equal. In this case, we basically need to specify whether we're doing a check against a type that we already know, or whether we're finding a new type and we don't care what it is. So this right arrow is binding a type. So we're saying we're going to bind two new types, T1 and T2. And this is checking a type. It says that this thing should have type T1. And that's how you read those. So it's not a direct translation, but it's pretty darn close. And so it turns out that this is real syntax. This is not pseudocode. You can write this, and you'll actually get a typed form which performs type checked application. So, and basically, if you want to extend it to multiple arguments, the Racket macro system is really good at like handling all kinds of different cases. And this is just the Racket macro system and the Racket templating language at play. So I can now just say, well, I want to extend this to n arguments. And by using these ellipses, these are not like indicators for code that's not on the slide. That's the real code. And you basically just say, oh, there's any number of these, 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 and it will automatically figure out, oh, the repetition is the same each time because you're using this pattern variable here. So it has to be the same number of repetitions as that one. And all this is very safe. This is all done completely statically at compile time, and it's all done using this like tower of macros that Racket has. So so this lets you implement all kinds of different things. Like here's an implementation of doing statically typed let. So here we have basically a pattern now, and we're saying, all right, here's let. We have x1 is bound to e1, and then we have the body, which is e2. And so again, we're just going to type check, or we're basically going to say, give us the type of this thing. E1 erases to E1 prime, and it has the type T1. That's the type that we infer for it, basically. Well, not really infer, but it's the type that it produces, because everything right now has static type annotations. And now we need something slightly more complicated, because in the body of E2, we need to, when we're doing the type checking, we need to know that X1 has type E1. So we're going to introduce another clause that says, all right, X1 erases to X1 prime. It has type T1 inside of this. So this is a binding. This is not an expression, and that's why we put it over here. And so this is kind of the typing environment that we're setting up, which again corresponds to the left-hand side of those typing judgments. And then again, we just expand into the untyped let from Racket. Any questions about this? Because I know that this is like a lot of stuff I'm throwing at you. You don't have to understand every single thing to understand like where I'm going with this.
No, but on the previous slide, there was the 3 dots are in between T1 and T2.
Yes. So the dots are a unary operator that applies to the thing just behind it, and this is something specific to the Racket macro system. The ellipses actually have like a very formal meaning. They're very predictable, and you can use them in very flexible ways. But so like if you're familiar with the Racket macro system, you'd already be familiar with this, but since you're not, then basically what this is saying is this is E2 repeated 0 or more times, this is T1 repeated 0 or more times, and then this is this whole clause repeated 0 or more times. And because of the fact that like it's a Lisp and everything is explicitly delineated, everything is explicitly marked with brackets and parentheses. That's easy to do. You don't have any like fixity, or you don't have any problems where you don't know what the operator precedence is, because you don't have that problem in a Lisp. So there you go. So that's that, but that's actually not really kind of the bulk of what I want to show off. This is kind of like the theory behind it. Well, I mean, it's not really the theory. It's what they've actually built.
I see the name turnstile showing up a lot there. I'm not clear how that fits.
Yeah, so this character right here is called a turnstile, and that's what they named their library.
Okay, so this isn't your library now. This is
not
macro library for description.
This is their library, and I actually kind of want to show off very briefly what using it looks like, because it's really, really neat. And what I'm getting to here is that I've implemented Haskell 98 effectively using this library.
Go for it.
And it is Haskell 98 with macros, which is interesting, and I'll get into why that's interesting. So, all right. So let's open, yeah, I will. Let's open a file here. Okay. So let's make that bigger. Okay, so this is Dr. Racket, which is the Racket IDE. You get it basically for free if you implement a language in Racket. It does really fancy things, like if you move your mouse over an identifier, it draws a line between where that came from. If you move your mouse over another identifier, it shows its uses. So this is really useful when you're writing macros, because macros can change the binding structure of your program in arbitrary ways. So it's sometimes unclear whether something's binding something or whether something's using something. But this tooling is really designed with macros in mind, so it'll show you information about what the binding structure of your program is just by sort of mousing over things. And if you click the little check syntax button in the corner, takes a little while because this is a particularly complex library. I'm actually not sure why it's taking this long. I'm not sure if it's even working. But anyway, there we go. It'll actually color your program based on some binding information that it knows about. But that's normally not such an expensive operation, but I guess this library is like really complicated, so it takes a little while. But the basic idea here is that this is the full definition in 35 lines of code of the simply typed lambda calculus in Turnstile in Racket. And so we can actually use this as it is, as a language. So this has only, it defines a type constructor with it, which is arrow for functions, and it defines a lambda form. It defines application, and it defines an annotation form if you want to have explicit type annotations. So all this is a little bit complicated, but again, it's the same idea, and this is using multiple clauses. So this clause is one with a lambda with explicit type annotation. So we're saying, here's the type binding for X, here's the type annotation for it, and these are kind of like type annotations, but they're actually not type annotations, they're parser annotations. So this is kind of like a domain-specific language using parser combinators for writing macros. So this is going to parse a type. This is going to parse an identifier. And so then we're going to do the typing rule, which basically says, all right, x erases to x prime. It has type t in, and then we're going to type check the body. It produces t out. I could go through this and make sure that everybody understands exactly what's going on, but I don't really think that that would be a good use of everyone's time. So I'm going to show you what using this looks like. So let's see. So this is turnstile, examples, STLC. Okay, so again, basically every program starts with this hashling line, which lets you arbitrarily customize what the language is for the module that you're writing. And this is very flexible. You can completely customize the syntax of your language, the semantics of your language, all kinds of different things. But in this case, we're just going to use an expression-based language that uses the simply typed lambda calculus implementation. So I'm realizing there are no valid well-typed terms in the simply typed lambda calculus because you don't have any base types. You don't have like integers or strings or anything like that. So you could have a function that returns a function that returns a function that returns a function, but you can never return anything real. So let's look at a language that actually has well-typed terms in it. And this is another thing that's cool about turnstile, is that we can just look at a language that extends the simply typed lambda calculus. So this is a definition of the simply typed lambda calculus plus numbers. So you can basically see that we're going to extend STLC. And we're going to, this is a 26-line module. It's really small. And what we're going to do is we're going to define a new primitive, which is going to be int, a new primitive type. And we're going to override what datums mean, what literals mean in our language. And we're going to say if it's an integer, we'll give it the int type. Otherwise, we don't support that kind of literal in our language. So like we're not going to support string literals. So now let's try using it. So I'm going to change this to plus lit. And again, we don't have definitions. We haven't given us the ability to create definitions or let or anything terribly useful, but we can create lambdas and we can apply them. So let's do that. So I'm going to make a really simple function that takes x and returns hello, and it's going to complain at me because again, we don't have type inference. So down here it's going to say no expected type. Please add some type annotations. All right, really cool. And again, this is like 35 lines of code. This is 26 lines of code. We have an online type checker automatically out of the box. So, all right, so I'm going to say, because we don't have polymorphism, we can't make this anything. So I'm going to say, let's make this a string. Or we don't have strings in this language. Let's make this an int. This is not a supported literal. Let's make that a number. Okay, so now you can see that this type checks, and it's really hard to see because this is so big, but there's a little green circle in the corner which says that everything expanded correctly. So now we can apply this. If I run this program, which I have no idea how long it's going to take. I don't know why this is taking so long, but maybe because I have another thing open. Let me try and close this. Okay, so this evaluated to a procedure. Obviously, it's just a lambda, which is not something that we can print in a very interesting way. But if we try and apply this to something like 0, and then we run this, then we get back 3, which is exactly what you would expect. We can also do something a little bit more interesting. We can make something that's an incrementing function. So let's add 1 to x, and this works. We can run this, and we get back 1. So this is all very interesting because these are well-typed programs anyway.
Where did plus come from?
That's defined in here, which is so this is basically saying export plus with a type annotation. So this is like a primitive operator in the language. We're reusing Racket's plus, but we're giving it the type int to int to int. So now what we can do is we can try and make this type, we can give it something stupid, like a function that takes no arguments and always returns 0. So now it's going to complain, type mismatch, expected int given arrow to int. And it'll even like give us a little syntax highlighting right here that shows us where the error happened, which is really cool. We didn't do any of that. It did that for us. All right, so this is obviously not super interesting because this is just the simply typed lambda calculus, which not a terribly interesting program. But there's a lot of different examples for all kinds of different things. I'm not going to go through all of them because most of them aren't that interesting. They're just implementing different kinds of type systems. But they include things like subtyping, polymorphism. There's an implementation of F omega, which is a type system that's actually even stronger in many ways than Haskell's type system. Haskell doesn't use it because its type inference is undecidable. But because it's explicitly type annotated, it's really easy to use. And Haskell's core language actually uses system F, or F omega under the hood. So
On your previous example, can you show what it expands into?
I can. So let me go back over here, and let's give it a well-typed program so it actually expands into something. And let's click macro stepper. All right, so this is another really fancy tool that, that Racket has, which lets you step through the macro expansion of your program. Now, this has 868 macro expansion steps. That's a lot. And that's, again, because this is a pretty complicated way of using the macro system. And it's all very new. Maybe eventually there will be some like better way to communicate with this macro stepper tool to like drop some of the unnecessary expansion frames. But if we just skip all the way to the end, you can see this is the fully expanded program. So this is if I click on these, this lambda comes from Racket base rather than coming from our language. So this is actually the Racket base lambda. And you can see that basically what we're doing, the Racket module by default will wrap every expression at the top level with something that prints it out, which is why we got that printing capability. You can override that if you want, but that's where this print values thing comes from. But the actual expression that we've got is we have an application of a lambda of one argument, and then we apply plus to 1 and x, and then we apply 0 to the whole thing, and that's what we got.
Is that getting interpreted or compiled?
That's getting compiled, and there's a JIT, it runs on a VM, it actually ends up being, so like the compilation phase for this is kind of slow right now because I'm running it inside of Dr. Racket, which compiles in a sandbox. It's a little bit faster when you precompile all this stuff. It's not too bad, but you can run arbitrary code. Like you can do I/O in the macro system if you want. Wouldn't recommend it, but you can if you want. So it can be relatively slow, but it's actually pretty fast for like most programs that I have ever written in Racket. Typed Racket is something that has like really forced people to make the macro expander faster because it does really fancy things. And this does really fancy things too. So these are kind of on the upper bound of some of the things that make the macro expansion a little bit slower. But honestly, it's pretty fast. Like it's fast enough to get real-time type errors. And what those type errors are, it expands the program in the background. It runs the whole macro expander. And then a type error is an exception raised during the macro expansion phase that communicates back where the source location was. So yeah, so every time it expands the program, then that's how long it takes to compile. So with that in mind, there's like a lot of different examples here, but again, most of them aren't terribly interesting. One of the ones that is kind of interesting is that there's an ML implementation. And again, this reuses a lot from other languages. It also defines a lot itself. I'm not going to explain how this works because like this is huge. I think this honestly is not like a perfect example of what this could be. This was kind of built and put together pretty quickly for the paper they're working on. So I'm not going to say that this is like a perfect example of how of great code. In fact, my background expansion ran out of memory to try to compile this program, which is hilarious. Most things are not this big though. And in fact, my implementation of Haskell I don't think is I mean maybe probably total, but I've broken it out into a lot of different modules. So, okay. So now that I've set up all of this context here, I want to talk about Rascal. Has a punny name, and it is a implementation of effectively a Haskell 98 in Racket. It actually doesn't use the turnstile library, but it uses the same techniques that turnstile uses. Eventually, I think I'm kind of working with them to figure out how to maybe make it so that we can use the same stuff. The turnstile library was built relatively quickly alongside this paper, but I'm using the same exact techniques. And so yeah, so the things that this supports right now, parametric polymorphism, ADTs, type inference, type-directed macros, and actually it does support type classes. I'm still working out a couple of the kinks, so I haven't officially put that in the list yet, but over the weekend I got type classes working. So I'm going to show off what that looks like. So again, this is all like super new stuff. I've basically implemented this whole thing in the past 3 weeks. So I'm not going to claim that this is great or stable, but this is an implementation of some of the Haskell prelude using Rascal. So it has ADTs. This is a really simple definition of unit using names instead of symbols because parentheses are obviously kind of important in Lisp. this is a definition of flip. So like, okay, I use Unicode symbols here partially because the original paper used Unicode symbols. I'm gonna replace these all with like words. Dr. Racket has like LaTeX inspired key bindings for typing these things, which makes it kind of easy to type, but like I wouldn't force everyone to use Dr. Racket. There's a really, really wonderful Racket mode for Emacs that uses like all the same tooling Dr. Racket does, so you get all the same fanciness if you use the Emacs mode, but I'm not going to force everybody to like type weird symbols. But I'm using it for now because it's easy and because I haven't changed it yet. So this is a definition for flip. I have explicit for all to make it cooperate more nicely with macros, which I don't think is too much of a price to pay. And you can see it takes a function from A to B to C and produces a function from B to A to C. And here's the implementation. Now, in my language, every function is curried. However, there's some sugar that basically when you write, because like if you wrote everything with like this in Lisp, that would be so many parentheses. So basically, if you apply a function to more than one argument, it's implicitly desugared into something that takes multiple arguments. So obviously, this is just a function that takes a function f, and because of the currying, this is really easy to implement. I basically just say, give me an f, give me an x and a y, and I'll apply the function, but with the arguments flipped. Similarly, here's id, which is even simpler to look at. Here's const. And so, if I try and like do something silly, like if I try and say this, it doesn't complain because of my bug in type unification. That was a really poor example. Let's do something else. This is also going to type check. This is a terrible demo. Let's give it like just a number. That will definitely fail. There we go. Could not unify. And obviously these like type variable names that get generated are terrible. And again, type errors are hard, but I'm going to make them better. This is like 3 weeks of work. The reason that this type checks is because right now I haven't implemented like rigid type variables, so this happily unifies this A with integer, and like the actual inferred type of ID becomes A to int. It should not allow that. That's bad. Like if you now try and use ID in another way, like if I say like X is a string and I give it hello, then apparently that works. I'm wrong, but I think the reason why is because I'm incorrectly using the type annotation the user provided instead of the one that was inferred. There's a lot of issues, but they're all fixable. So anyway, moving down, this is kind of the more interesting stuff. So here I'm actually defining a type class. This is the standard definition of functor. So again, we've got a map, and this type signature looks kind of ugly right now because I haven't added sort of the sugar for infix operations right now. So you kind of have to use prefix arrows for curried functions, which looks really gross. But that's really a syntactic thing. That's not too hard to add. But you can see that it's basically given a function from A to B and a functor of A, you can get a functor of B. Really simple. Here's a definition of infix fmap. I'm not really totally sure why I define this because there's no actual syntactic definition between infix operators and prefix operators in this language, but I figured I would define a bunch of different things just to kind of test it out. And in this case, I can actually demonstrate that my type checker is not a total lie, and I'm not deceiving you. Because if I remove like an argument here, then it's going to complain with a horrible type error that doesn't even fit because my font size is really big. But if you actually run the program, it'll give it to you, but I'm not going to run the program because I don't know how long the compilation of this will take, given that I haven't precompiled it, and this is the whole prelude. So moving on, we've got applicative, we've got pure, we've got apply. All these names I'm just kind of stealing from Haskell. I don't know if I would actually call them the same thing because the syntax is different, and I don't know if infix operators make the same amount of sense. I am kind of reusing the Racket infix syntax here, which is like if you put 2 dots around a thing, then it will be used, it'll be read as an infix operator, which basically just moves this to the beginning, and otherwise it's the same. This is ugly. I will come up with a better infix syntax eventually, but it looks okay. It's like actually not that bad because if you look at the definition, this is sort of the apply but ignore the left argument. So you can see this takes an applicative, given an f of a and an f of b, you just get back an f of b. And so you can see that I'm basically creating a function here which ignores its first argument, always returns its second argument. I'm applying it to f of a and then applying it to f of b, applicative style. So, and that's all type checks. Here's the one for reverse, and now here's monad. Now I haven't implemented, one thing you may have noticed, I have not implemented superclasses yet. That's actually not really a type checker feature. It's more of a, I mean, it is a part of the type checker, but it's really trivial to add. It's more of just like an additional pass in type checking the constraints, which is not hard. I just haven't done it yet. But I also haven't implemented default methods yet, which is a lot more complicated. Not, again, because the type checking is hard, but because compiling default methods is complicated and doing the verification of minimal instances. So I haven't gotten there yet. But so in the meantime, I'm just basically defining join instead of bind, because I think that that's a more useful definition of, or a more understandable definition of what a monad is than bind. But I can define bind in terms of join really easily. Specifically, I'm defining reverse bind here as a function f, m, join, fmap, apply fmap f over m, join them together. And there you go. And then that's your definition of reverse bind. This is just flip of that. And here's app, which again is just the applicative apply implemented using monadic operations, which turns out to be relatively useful in practice because a lot of the time you just want to implement monad and not applicative, but you have to because applicative is a superclass, and you can use app to get an implementation of applicative for free effectively. Okay, so that's the boring class definitions. Here we've got a definition of bool. Here we've got a definition of not. This is really simple. This is showcasing the pattern matching. So again, basically this is just saying if it's true, give me false. If it's false, give me true. And this, of course, works with the fancy binding arrows because Racket is cool. And I really like mousing over these things. I think it's pretty and it's kind of entertaining. So moving on, maybe. So this, now we're actually going to get into something that creates instances. So here we've got the actual definition of maybe. We're doing case analysis. Here's functor. Given that it's just x, then apply f to x, otherwise return nothing. This is all really simple stuff if you're familiar with Haskell. Here's the monad definition. Here's either. Now, using some of this, I can also define list, which is a recursive data structure, which works fine. And I can implement fold, I can implement reverse, and I can implement the functor instance, and using all of these things combined, I can partially apply string append, and I can map it over my list, which I don't have any syntactic sugar for yet, so I'm just spelling out cons. But I can now run this, and this is actually kind of taking a long time. But, oh right, I have a bunch of debugging stuff that I totally forgot I haven't taken out yet. Well, that's exciting. But if you look at the end here, you can see it actually does print out the result. And right now, main, I don't have I/O yet in my type system, so I'm just kind of printing out whatever you give to main just to kind of debug. But you can see that it actually maps this sort of string append for prefix over this list, and it works. And the reason that this is really cool is because type classes like this are impossible to implement without a type checker anyway. So you can do dynamic dispatch. In this case, you could emulate it with dynamic dispatch. I promise you I'm not doing dynamic dispatch here. This is actually properly doing the type class elaboration, figuring out the static types of all these different things, and then generating the right application statically. Well, it does dictionary passing like Haskell does, but statically it determines what the types are and uses the correct implementation. One thing I am working on that I haven't gotten, which would have been a cool demo, is type tooltips. It turns out that like adding tooltips is really easy with a macro system because you can just at any point in time say, oh, I know the type of this. I'll like put a syntax property on this piece of syntax that then Dr. Racket will turn into a tooltip. I didn't get that working quite yet, mostly because it turns out to be complicated when you have type tooltips that overlap. But I haven't fixed that just yet, but it's totally feasible. So there you go. So that's what I have so far. Now, why is this interesting? Why, as a Haskell programmer, should you care at all? Because honestly, Haskell syntax is way prettier than this. I'm just going to be honest. I don't like parentheses for the sake of parentheses. Haskell syntax is way more readable than this soup. But what I found in my experience is that there's a trade-off. When you have a uniform syntax like this, it's really easy, really easy to write macros. And what this means is that you end up writing less code. So the syntax is a little bit less pretty, but there's no boilerplate because that all gets abstracted away into syntax transformations. So as an example of this, algebraic data types are a primitive in, as far as I can tell, any language with them that I know of. they're not in this language. They are a library. You import them, and like they are not supported out of the box by the base type checker at all. So they're kind of a complicated, hairy macro, because implementing algebraic data types is a little bit complicated. But this is actually the implementation of ADTs. So I'm going to go down to the definition of data. And it's right here. So basically you can see this is just an ordinary Racket macro that takes sort of the name of your type, it takes a constructor, and it defines a new base type. Now base types are something that again are known by the type checker, but they're like I can just basically define them as I please. This arity is probably eventually going to be used for kind checking. I don't actually have kind checking yet. I didn't say that. But so right now, like if you have if you improperly apply a type, you'll get a type mismatch, but it won't give you a kind error. It's really more an error reporting thing. It turns out that like it will basically just complain that you don't have a value of maybe. Like maybe doesn't match with maybe int, which is obviously bogus because like maybe is kind star to star. It should not be a value at all. It should not be a valid type to apply to a term, but it turns out to not actually be a soundness hole at least. So, so again, and then this keeps track of some static information, which is the number of constructors that it has, which is used for pattern matching. And this is just like an arbitrary piece of data that I attach to this type, and then I can pull back out later. So these constructors themselves are defined right here. So I have a much more complicated macro called define data constructor. And what this does is it generates a bunch of fresh type variables. It evaluates the types that you provide it to get actually like the type representation in the language. And depending on whether or not it's a nullary type, it defines a value or a function. And so this does a bunch of different checks, and then it expands into some racket that actually implements it all. So again, this is a lot hairier than some of the other stuff because, you know, algebraic data types are complicated. But a lot of this isn't actually type checking logic. This is compiling ADTs. The type checking logic is pretty much entirely in case right here, because this is what actually, well, there's two parts to it. One, we have to assign the type to each thing that we create, which is not hard. We just assign the type, we instantiate the type of the value that we get, which is defined right here, which is the generalized type of inferring what the type is from this tag, which is just the type that we give it. It's a little bit wordy, but basically we're actually just doing a really, really simple type expansion there. And then we do type checking in the case. And so I don't have exhaustiveness checking. I used to before I made patterns a lot more general. But if you use something that's like a total lie, like if you try and match against nothing in case here, then it will obviously complain, could not unify maybe with either. That's a bad type error. Like obviously the error message could be better, but it does actually do the type checking there. And yeah, and so this is all just a macro that's basically re-provided by the main language. So if I look at private, or let's look at Rascal main, there's basically two things that implement all of this, which is ADT and base. Base defines all the type checker logic. ADT implements ADTs. They don't talk to each other. They just kind of work. So why is this interesting? Well, there's a lot of things in GHC that are primitives. Generalized new type deriving is an example of that. Type equality is an example of that. Things like generics are an example of that. And lambda case. I mean, lambda case is a trivial macro in Racket. It's a lot. In fact, I could implement it right now. I probably don't want to subject you all to more like parentheses, given that that's not what I'm guessing that you signed up for. But but it's really trivial. Do notation is a trivial macro, and in fact, I can show you a demo of that. Actually, let's do that. This is not implemented in Rascal. This is actually the do notation that I implemented in sort of untyped Racket, but the macro looks almost identical. So this is the whole definition of do. It's about 12 lines, and you can see that basically all it does is it says, well, if there's an arrow here, then convert it into a chain call, which is what I called bind in this particular library. And otherwise, just if there's only one thing, expand into itself. If it's an internal definition, like an internal let, don't do any binds, just expand out to it. And that's it. That's all of do notation. Like, and this is really neat because if you have new stuff like arrows, you don't need to go to Simon Peyton Jones and ask him to implement your like fancy arrow do syntax or applicative do syntax or all those things, because again, these macros as with the algebraic data type implementation, they can be type directed. They can influence the type checker. They can get information back from the type checker. So you can actually define macros that will do things depending on the types of the individual terms you give them. So this is obviously a lot nicer than, say, template Haskell, because template Haskell is really restrictive in the sense that, one, it's not a macro system, it's a syntax generation system. You don't give it syntax, you give it like ordinary values and it will generate syntax. Macros are a syntax-to-syntax transformation, so you can implement things like do notation. You couldn't implement do notation as a template Haskell function because template Haskell can't define its own syntax. Similarly, you couldn't do a lot of these things with GHC generics because generics are a read-only thing. You can't influence the type checker. You can get information from the type checker. You can't influence the type checker. And so I think that like for a lot of these things, it's kind of an open area of research to see how much can be defined outside of the core, how much has to be defined inside of the core. Things like Rankine types and multi-parameter type classes will almost certainly have to be a part of the base type system, but maybe not. Maybe we can figure out a way to avoid that. So I'm kind of gonna see, but I think in the meantime, the idea here is that you can get all the static guarantees that you get out of Haskell, you can get all that fanciness, but you also have access to a safe macro system that isn't going to be a foot gun as a lot of other macro systems are. So that's really about it.
So like you were talking about how it can sort of influence the type system, but also read from the type system.
Yep.
It seems like one foot shooting sort of situation would be if you have sort of a loop of dependency where I'm sort of pushing and pulling against the type system.
Yes, so basically that can't happen, and the reason it can't happen is because you'll get an error if you try and do that. And the reason for that is reading from the type system basically is not, it's not like a magical thing where you say, hey type system, give me some information. It's you call a function that expands an expression and gives you back a type from it. And then you can expand to something that then like assigns a type to something. You can't like depend on your own result because the only way to communicate, like the output of a macro is expanded syntax. Yeah. Now this is actually kind of a problem to some extent because then how do you have mutual recursion? How do you have especially mutual polymorphic recursion? And it turns out that you can, by limiting what people, like you can say like all these things that are defined together, I can type check them all at once. I can sort of say like group them up, infer all the types, spit out some results. But if you have like an instance definition or a class definition and then you've got a bunch of functions and then you have an instance definition and another bunch of functions, how do you make sure that the macro expansion order is right such that everything gets defined at the right time? And normally this is not a problem in macro systems because the way macro systems work is they start at the top, they like expand things and they go down, and if they get stuck, they try expanding something else and they kind of move around. In order to get the type though, you have to recursively expand the type of some whole expression tree. Because inherently, like you don't know what the type of some polymorphic function will be until you instantiate it, which might require like walking the whole tree down, getting somebody type the number 1, propagating that int back all the way up. So that's kind of another open problem of like how do you do partial expansion in a way that lets you have mutual recursion in as flexible a way as possible. I get the sense that it probably can't be done completely arbitrarily like it can be in Haskell, because in Haskell everything's known statically. In this system it's not, but so far like all of the common, like it turns out that mutual recursion really only happens in a couple of ways, and they're almost always like two functions that are defined right next to each other, because if they're mutually recurring they have to be in the same scope. So being able to handle those is not too hard, but it is something that's like a valid point. It's a little bit trickier than it might seem. So yeah.
One thing I was wondering about was you showed the ADTs briefly. I was curious how they were encoded. So that code has to do sort of two things. It has to deal with the typing them and also has to translate them into the underlying.
Yes. Yes, and that's kind of the. Well, it translates them into Racket.
Racket.
Now, this is not the system that this like technique is not actually tied to Racket. One of the things I want to do, like I actually legitimately want to do, is expand to, because this basically just expands to a bunch of primitives. Those primitives are given meaning by Racket, but they could be given meaning by other things. I want to compile to GHC core. I actually really want to do that. That's something I don't anticipate being able to do for a while. But then the question is, why not just make list flavored Haskell, right? And the reason is you have to have a separate type checker to do the types interleaved with macro expansion thing, because otherwise you only get to expand your program, give it to the GHC type checker. So for that reason, like the interop story might be a little more complicated. But I do want to do that simply because you can get really good performance. GHC is really good at optimizing for these types of things already, and also because then you could have interop with the rest of Haskell, because this is effectively just Haskell's type system. And also maybe target JavaScript at some point. But it is sort of independent of the representation. But it is true that the way this system works, and it's actually kind of the crux of how this system works, the type systems as macros approach, is that every macro does two things. It type checks and it expands. So the input to any macro is an expression, and the output is, well, it's
an environment, right?
Well, it's actually not. The environment is actually tracked automatically by lexical binding in the program. The macro system handles that for you. So it's kind of implicit. Yeah. Yeah, it's kind of, I mean, it's a little bit more interesting than that in some respects, but I won't get into that. But yeah, so you give it an expression and some kind of implicit binding or environment, and then it outputs expanded, erased expressions, and types and constraints and predicates and all of those things. And then, I mean, again, and then the other thing is that, like, because this is just macros, you can do totally arbitrary things to the type checker. In fact, you could write you could probably write, in fact you could implement unsafe coerce as a macro. You could say, well, here's a macro that takes anything and produces anything, because you can outright lie to the type checker. There's almost no guarantees right now. There's no checks to make sure that the typing rules that you are building make any sense.
You could probably do that by then having the thing you expand to be itself typed or something, right?
So to some extent, there are some validations you could do. But I think on some level, it's not a completely solvable problem, because like implementing ADTs is coming up with a bunch of new typing rules. And I don't know if typing rules is
be able to like prove that it would always produce a type.
Yeah, you could maybe couple it.
Yeah.
You can maybe couple it with a proof assistant. Yeah, and that would be interesting. But it's not something that I've even looked into at all.
Quickly, a lot of these questions, the answer starts to become like halting problem.
Yeah, it is, and to some extent, you know, I mean, like types attempt to solve the halting problem by restricting the domain, which is, you know, kind of the whole point. You can't solve the halting problem in general, but if you don't have X things, you can solve it in a lot of cases. But it turns out to be a little bit hard. So yes, that's a good question though. Anything else? I hope that wasn't too painful, given all these silly parentheses from my silly language. That's a Lisp.
Painful for SC Max users.
Yeah. But anyway, that's all I got. So thank you. Thank you for sitting through it.
Does anybody else have anything they want to that they've been working on they want to show for? Yeah, no?
To Haskell towards the end. This is not my talk, as you can see. This was given at RacketCon 2016 in September, last month. but I'm going to give it because it's something I have. So basically, Racket, as I've kind of mentioned, is a programming language for creating programming languages, and there's ways to sort of reuse existing constructs. So all these things are sort of like core primitives that you can overload. And you also have the ability to just arbitrarily customize the program semantics, the reader. There's like Algol60 is a language in Racket. JavaScript is a language implemented on Racket just for fun. There's Prolog implemented in Racket, but the main language is the Racket language. So it's kind of two things. It's a language and a Racket and a language platform. And that's a scheme descendant. So Racket really focuses on linguistic reuse. And so basically the idea is if you are interested in building a language, rather than having to build out an entire compiler with compiler architecture, you can just start with something that already exists. And all these languages can kind of talk to each other at a pretty high level, which is really nice. So this is a really simple diagram of, it's a little bit hard to read because it's relatively small, but the basic idea is that these are all the different languages that are in language that has only two primitive forms. So what we want to be able to do is type check this. We want to create the simply typed lambda calculus. And it turns out that this is actually really possible to do, but what we want to be able to do is just basically translate the STLC typing rules just from the typing judgments and figure out how to turn those into macros that will actually perform type checking. And it turns out that we can do this. And so it looks kind of like this. This is an example of the type checked application form. Now it looks kind of complicated and it looks nothing like that typing rule, but it does actually correspond. So the basic idea here is what we're going to do is we're going to type check the type, we're going to get the type of E1. Yes?
What's the procedure for reading those symbols on the right?
Which?
So that block, like
this
gamma.
thing? This is just like on the slide. This is just on the slide. It's not actually source code. This is the source code.
So I'm not supposed to understand that thing.
No. This is the typing judgment. If you're not familiar with like typing rules, that's totally okay. I actually had no knowledge of type theory before I started working on this. So I'm about a month in, and before that, when I saw this talk, I had no idea what any of these meant. So no, you don't have to understand that. All right, so I'm going to assume everyone in this room is familiar to some extent with Haskell, but I don't know if everybody has even heard of Racket. I guess raise your hand if you have heard of Racket. All right, has anybody here written any Rackets? Written a little bit. So it's a scheme descendant, but it's very different from, I think, a lot of Lisps. It's not really a language, it's more of a language platform. And so there's been a lot of research into figuring out how to build languages really, really, really fast with using Racket, and one of Racket's main components is this macro system. And it's a very safe macro system. It's really kind of cutting edge. There's a lot of type systems in the world. You can really make arguments about which one's the best. There's kind of a lot of orthogonal type systems. But Racket's kind of indisputably has the best macro system in the world. It's really kind of, there's no competition. There's about 20 years of research going into it. So because of that, one of the things that, this is very, very new research. This is being presented at POPL 2017, type systems as macros, and it's figuring out how to, as the name would imply, embed type checking into macros. And I'm going to kind of connect that. The way typed Racket works is you have your typed program, you expand it out, you type check the fully expanded program, and then you run the result with the types erased. So that's a pretty standard way. Aside from the macro expansion pass, this is a pretty standard approach to doing type checking. And so basically, the trouble with this, of course, is that this takes a monumental amount of effort to build. It took years of work. And it's really not possible to reuse, whereas you can reuse faculties from other languages in dynamically typed Racket languages. It's really hard to reuse pieces of the typed Racket type system. So the alternative approach, which again is very, very new, is basically figuring out how to make macros interleaved with type checking. So macros actually do the type checking as well. So you kind of, instead of just having the type checking at the very edge of the program, we push it in to as the program expands. So what this lets us do is basically define, this is an example of defining sort of a simple lambda calculus language. So we have a lambda, which binds an x and produces an expression. And this will just expand to the Racket lambda. And then we have sort of application, which has 2 expressions, and we'll just expand into Racket's application. So this is obviously not very interesting because we're just basically reusing the Racket host language semantics. But you can see that we've come up with like a really simple language in the core of Racket. And if you look, there's a black, which is everything else. So this is not actually all of them. But these are all the languages used to implement the core of Rackets. And so these all talk to each other. They all interop very, very nicely with one another. And so the idea is that you pick a language for your specific tool. So languages are just libraries in Racket. And you can use many of them together to make one program. So there's a problem, though, with these, is that every single one of them is untyped. There's actually one typed language in the Racket ecosystem, which is called, not too surprisingly, typed Racket. And it's a gradually typed version of sort of the Racket language. It does static type checking as a macro expansion pass. And so the way it works is basically you have one big macro that wraps your program implicitly. You expand all the user macros, you check the types, and then you get very strong static type guarantees that you would expect. But it's designed to be gradually typed, so you don't get things like type classes. You don't have unification-based type inference. It's really just designed to be, the flow type system, if you're familiar with the flow type checker for JavaScript, is based on a lot of the research that went into typed Racket. So the question is, can you come up with typed languages in Racket, or is it really only good for one thing? And the good news is, you kind of can. So again, here's kind of a diagram of the